eigenvector and eigenvalue of a vector space. At first, let's see some example of linear transformation. Because I have told you many times, linear transformation are very important for any competitive exam. At first, see some example. Then I will discuss what is the eigenvalue and eigenvector of linear transformation. First, consider the function as a multiple variable. Consider the function from Rm to Rn, where x belongs to Rn. Then fx, obviously since the function is Rm to Rn, obviously fx would be f1x, f2x up to fnx, where x belongs to Rn. Then this f is linear when each fi would be linear, where fi means each fi map Rn to R for all I. That means for multivariable calculus, a function be linear or non-linear. This will be evaluated by when each component be linear. Are you getting? Well, and the proof is very easy type proof. Consider for all I, each fi be linear, then obviously fx equal to f1x up to fnx. Then we have to prove f be linear. That means at first we have to prove f of x plus y equal to f of x plus f of y. F of x plus y means obviously f1x plus y up to fnx plus y. And by the property of linearity, since each fi is linear, I have assumed. That means from this expression, obviously since f1 is linear, then this would be f1x plus f1y. And since similarly fn is linear, then this would be fnx plus fny. Therefore, this just arrange it very clearly. Consider this is f1x up to fnx plus f1y plus f2y up to fny. And this is actually fx, and this is obviously this part means fy. That means f of x plus y equal to fx plus fy. Similarly, f of tx would be t times f of x. This similarly, or all property of linearity has satisfied here. That means if fi is linear, then obviously f is now linear. Let's see some example. Consider f from R2 to R4 such that f of x comma y equal to x plus 5y comma x comma y comma x plus y. Is it linear? Have to check each fi be linear. For this, we all of us know any linear map. If we consider R2 to R2, consider 3 arbitrary number a, b, c, d belongs to R, then any linear map from R2 to R2 of the form f of x comma y equal to ax plus by comma cx plus dy. And notice here f1, f2, f3, f4 is such type. So obviously this mapping is linear. Consider another linear transformation f from R2 to R4 such that f of x comma y equal to x square comma xy comma x plus y comma 5x. Is it linear? Notice here x square and here xy. Obviously these two term is linear, but is this two term be linear? For this, if we consider one mapping T from R to R such that T of x equal to x square, then obviously T is not linear map, because T of alpha x equal to alpha x whole square, which is equal to alpha square times x square, and x square means obviously t of x. That means this is equal to alpha square times t of x. That means t of alpha x not equal to alpha times t of x. So x square cannot be linear transformation. Similarly, xy cannot be linear transformation. So this mapping be not linear. Are you getting? Oh well. Now I will see some linear transformation. First, reflection with respect to x-axis. For this, consider T1 be the map from R2 to R2, defined as for all xy belongs to R2 such that T of xy equal to x comma minus y. This is very easy to check, and this linear transformation is, geometry is, reflection with respect to the x-axis. Here x comma y map to x comma minus y. Now I will see another linear transformation, reflection with respect to y-axis, and the mapping is such type T2 be the mapping from R2 to R2, defined as for all xy belongs to R2, T2 xy equal to minus x comma y, and this linear transformation be reflection with respect to y-axis. Are you getting? Now I will see one linear transformation such type T3 be the map from R2 to R2 such that for all xy belongs to R2, T3 xy map to 0 comma y, and this linear transformation is actually projection on the y-axis. Okay? Now I will see another type of linear transformation on R2, reflection with respect to origin, and this linear transformation is denoted as T4. Consider T4 be the map from R2 to R2 such that for all xy belongs to R2, T4 xy equal to minus x comma minus y. Notice, this is the linear transformation, and this is actually the reflection with respect to the origin. Now I will see another type of linear transformation, projection on the x-axis, and this linear transformation is denoted as T5. Consider T5 be the map from R2 to R2 such that for all xy belongs to R2, T5 xy equal to x comma 0, and this mapping is actually projection on the x-axis. Are you getting? Now I will see another type of linear transformation, rotation by an angle theta in the counterclockwise direction, and the mapping is denoted as T6, which be the mapping from R2 to R2, defined as for all xy belongs to R2 such that T6 xy equal to cos theta x plus sin theta y minus sin theta x plus cos theta y. I will highly recommend you, please pay attention geometry of this linear transformation, because this linear transformation actually very important for higher study, and by this linear transformation we can easily generate one matrix which matrix be reflection, projection. By this linear transformation we can tell easily. Okay, so these type of linear transformation are very important for higher study. Now I will see two transformation. First transformation, consider AB M2R, and the mapping is such type phi M2R to R such that phi of A equal to determinant of A. And second mapping is A belongs to M2R and phi of M2R map to R such that phi of A equal to trace of A. Is both mapping is linear? us notice here phi of A equal to trace of A. Then by the property of linearity, phi of A plus B equal to trace of A plus B. And by the property of trace, we all of us know this is actually equal to trace of A plus trace of B. Okay? And this trace of A means phi of A. And this trace of B means phi of B. And phi of C here alpha A equal to trace of alpha times A. And by the property of trace, this means alpha times trace of A. Okay? Therefore, both property of linearity has satisfied here. Phi of A plus B equal to phi of A plus phi of B, and phi of alpha A equal to alpha times phi of A. Are you getting? That means obviously this mapping be linear mapping. Second, here the mapping is defined as phi of A equal to determinant of A. That means the mapping is such type A, B, C, D be the mapping equal to AD minus BC. Is this mapping is linear? Notice phi here M2R is isomorphic to R4. We all of us know. Therefore, actually A, B, C, D is similar to in R4 A, B, C, D, and we all of us know R4 to R, the linear map is look like first degree polynomial with zero constant. But notice here this is not first degree polynomial, this is second degree polynomial. So this mapping be not linear. Are you getting why any linear map Rm to Rn is very important? Since we all of us know what is the type of linear map Rm to R. So I have treated this method because we all of us know M to R is isomorphic to R4. Okay? Now I will see one interesting linear map. I will see in linear mapping why field is very important. The mapping is such type F from complex number to complex number such that Z map to Z bar. That means x plus iy map to x minus iy. And the mapping is such type fz equal to x minus iy. Here notice that means the conjugate mapping. This means the conjugate mapping. F is linear over the field R. But if we consider C complex number, then F is not linear over the field complex number. Why? Just think. Proof is such type. Consider two arbitrarily complex number. Consider Z equal to x plus iy and w equal to u plus iv. Then Z plus w means obviously x plus u plus I times y plus b. And f of z means x minus iy and f of w means u minus iv. Then what is f of z plus w? F of z plus w means, since the mapping is conjugate mapping, that means here only conjugate minus, and f of z and f of w means this, then f of z plus f of w is x plus u minus I times y plus b. That means this is similar to fz plus fw. That means f of z plus w is equal f of z plus f of w. Now I will see scalar multiplication. Consider the scalar from real number. Then f of alpha z means alpha x minus I alpha I, which we can write as alpha times x minus iy. That means this is actually alpha times fz. That means obviously f of alpha z equal to alpha times fz. Here I have considered alpha from real number. But now I will consider alpha not belongs to real number. Since alpha belongs to C, so we can consider I as a alpha. Then f of iz means obviously minus y minus ix, and f of z equal to x minus iy. Then I times f of z means I times x plus y iy, which is equal to ix minus iy. That means, notice here f of iz not equal to I times f of z. Are you getting? That means if we consider the scalar as a complex number, then this property will not satisfy. So conjugate map is a linear over the field real number, but not linear over the field's complex number. Are you getting why field theory is very important for any mapping? Let's come back our original discussion, eigenvalue and eigenvector of a linear algebra. Eigenvalue and eigenvector represent an useful concept in linear algebra, and not only linear algebra, whole mathematics and mechanics, physics, all of the stream. Let's see at first what is the eigenvalue and eigenvector of a linear operator, because here I have discussed about linear algebra. For this, consider VBN vector space over the field A. Then consider T be a linear operator from vector space to itself. Then a non-zero vector which is denoted as small v is said to be an eigenvector of the linear operator T if there exists a scalar lambda belongs to field such that Tv equal to lambda times v. Then the scalar lambda is called eigenvalue corresponding to eigenvector v. Are you getting? What is the eigenvalue and eigenvector of a linear operator? OA. As for example, consider a matrix A, then a non-zero vector v is said to be eigenvector of the matrix A if this v is an eigenvector of a linear operator who is denoted as LA from Fn to Fn, such that AV equal to lambda times V for some lambda belongs to F. And AV equal to lambda times V means this is look like a function. This is look like the function fx. Means here the input is V and act on A, then I will get the output AV. And AV equal to lambda times V. That means this output would be such vector which are actually parallel to V. Are you getting? Then the scalar lambda is called eigenvalue of the matrix A corresponding to the eigenvector V. And these eigenvectors and eigenvalue are called characteristic vector and characteristic value. So actually the geometric interpretation is the vector AV is parallel to the vector V. Here we can allow, obviously, AV equal to lambda times V means we can allow the direction same or opposite direction. And this value of lambda may be different. Lambda may be 2, 3, 5 or complex number, and when lambda equal to 0, then AV equal to 0, and AV equal to 0 vector means obviously this eigenvector V contains the null space of A. That means eigenvalue equal to 0 means V contain null space of the matrix. Okay, and eigenvector contain the null space of the matrix A means obviously the matrix A would be singular. That means when the matrix A is singular, then eigenvalue always 0 and eigenvector contain null space of the matrix A. That means if there exists a linear operator T from vector space to vector space such that TV equal to lambda V where lambda not equal to 0 and where lambda be member of field, then we can say this lambda is eigenvalue. Suppose for a given fixed lambda which is eigenvalue, I will get Tu equal to lambda times U. Then not only U, also 2U be the eigenvector because T of 2U would be lambda times 2U by the definition, and notice T of 2U means 2 times Tu, which would be 2 times lambda U, and from this line we can write this expression. So if U be eigenvector of any linear operator, then 2U also eigenvector, and not only 2U, every non-zero scalar multiple of U is an eigenvector. Are you getting? Oh well. That means the actual idea is for a fixed lambda, collect all the eigenvector corresponding this lambda, and this is actually a set. This is the picture and this is the collection of all eigenvector corresponding to this fixed lambda, and this is obviously a set, and not only be set, this is actually be the subspace of this linear transformation. So there exists a theorem, consider T be vector space to itself, be linear operator and lambda be scalar, then all vector with TV equal to lambda times V always be a subspace. And the proof is such type, let V1 and V2 be two vectors in the set such that TV1 equal to lambda times V1 and TV2 equal to lambda times V2. Then T of alpha V1 plus beta V2 equal to, by the property of linear transformation, this is equal to alpha times TV1 plus beta times TV2. And obviously TV1 means lambda times V1. That means put the value. And TV2 means lambda times V2. Then omit, since this is lambda is scalar, then omit lambda. Then this would be lambda times alpha V1 plus beta V2. That means apply T on the vector alpha V1 plus beta V2. I will get multiple of scalar of this vector. So obviously TV equal to lambda V, this set always be from a subspace. Are you getting the idea? Oh, geometrically, eigenvector of a matrix means non-zero vector in Rn such that the vector V and AV are parallel to each other. And algebraically, how we will find the eigenvalues and eigenvector of an linear operator? We will use matrix representation. For this, choose a basis B for the vector space V. Then find the matrix representation with respect to the basis vector. Consider AB n cross n matrix and lambda be scalar. Then Obviously lambda is an eigenvalue, imply there exists non-zero v belongs to Rn such that AB equal to lambda times v. That means from these lines there exists non-zero v in Rn with the condition A minus lambda In times v equal to 0 vector. That means that imply non-zero solution of the null space of A minus lambda I. Because here A minus lambda In v equal to 0 vector. That means A minus lambda In is not invertible. And this condition is always if and only if condition. Are you getting? Oh, idea. I will see one nice theorem. Let A be n cross n matrix over the field A. Then lambda belongs to A is an eigenvalue if and only determinant of A minus lambda In equal to 0. Are you getting? And this is actually would be one polynomial of order n, since A be n cross n matrix, and this polynomial is said as characteristic polynomial, which I will see in my next video. And eigenvector of A corresponding to lambda, precisely actually the non-zero vector of the kernel of A minus lambda In. And this is actually called as eigenspace associated with lambda. Are you getting? Oh, I will stop here. In my next video, I will discuss some example of eigenvalue and eigenvector geometrically. So, stay safe and stay positive always.